Hello everyone, welcome to this video. In the last video we talked about how to create a spectrum analyzer using ADALM-PLUTO. The way we did it in the last video was using a mixer at the receiver to downmix a signal, the received signal, then convert the baseband signal in time domain, which is recorded by our ADC to frequency domain using a Fourier transform. Now we want to take a look at the second approach, which was sweeping the LO frequency, then extracting the DC value after each time we change the LO frequency to create the spectrum of the signal. In this video, we want to go deep to see how this works, see the math behind it, and then uh, use our Pluto to create that, and finally see some cool examples of using this in real applications. So, what's the problem? Assume we have a signal that a sine wave signal with a frequency of f1 and amplitude of am. And this signal has a phase also has a phase. We want to be able to extract the phase and the amplitude of this sine wave. If we want to expand this, we can go saying that assume that we have our signal has different sine tones at different frequencies, f1, f2, f3, and we want to be able to extract am1 phi 1, AM2, phi 2, and AM3, phi 3. Among all these different frequencies, and also assume that we have even noise in here, and we want to just lock in a certain frequency of our interest and extract the amplitude of and phase of that signal. But let's start with simple solutions to this problem. One way to is to if we want to just extract the amplitude of this sine wave. In AM radio, AM stands for amplitude modulation. Uh, Basically, the signal, the data is uh, is in is stored in AM in this amplitude of this sine wave, which is our carrier frequency. And usually simple radios uh, want to just extract the amplitude and use that amplitude, feed it to a speaker, and see the demodulated data. That's one of the ways. So a very simple solution, very popular one. Here I'm just showing the circuit. As one of the simplest circuit solutions is called peak detector. Basically, what it does is that let's assume that sine wave is at our input, right? We want to be able to extract the amplitude of this sine wave, just the amplitude. We can use a diode. Here I just used a very idealized diode with with zero forward bias voltage, meaning that there is no voltage drop. If the diode is uh, if the diode is conducting, we don't see any voltage drop from V in to V out. So how does this work? In the negative phase of the input, assuming that our V out is zero, the diode is biased reversely. So it doesn't conduct any current. It just is will be seen as a very high resistive resistance, right? But then as soon as the amplitude becomes positive, Vin becomes positive, this diode starts conducting. And when it's conducting, it just starts passing current through it. And Vin will this current will start charging this capacitor up to, and V out starts tracking V in. You can see here in the yellow plot, we start tracking our sine wave until its peak. Then after the peak, because now V out is equal to our peak value, V in starts going below our peak, meaning that now again our V out is higher than our V in. So our diode stops conducting. So when it stops conducting, no current goes pass through, and we just have, if this resistance is high enough to not uh, discharge this capacitor, our V out will store our amplitude value, right? So now we can see how we can extract the amplitude value using this method. Based on the time constant of our load, we can select how what the decay ratio of this amplitude detector, because in real AM radio, this amplitude also may change, and we want to keep track of the peak value of the input sign, right? So we need to adjust the time constant of this circuit. But this is going to be in another video, that we are going to actually build the AM radio using a very simple circuits on in and test it in real world. Okay, now let's talk about the second approach, which uses some signal processing to extract the information. If you notice in the last approach, we were able to extract AM, which was the amplitude of the signal, but not its phase. Now we want to do some signal processing to not only extract the amplitude, but also extract the phase. We define SI equal to our signal multiplied by sine of 2 pi ft f equal to the frequency of our desired signal, right? The frequency of our received signal. We basically lock the sine wave frequency to our to our received frequency. What happens here, we can do some equations, some math equations to convert this multiplication to a subtraction. Sine A multiplied by sine B becomes half of cosine A minus B minus cosine A plus B. If we use this, we will end up with AM over 2. Now, this term minus this term, 2 pi ft plus phi minus 2 pi ft. The second term minus cosine of this term plus 2 pi ft, which will end up in this equation, AM over 2 cosine phi minus cosine 4 pi ft plus phi. Now we have an interesting situation, because we have a DC signal, meaning that it's a constant, it's not changing over time, added to a time varying a signal that changes over time, right? With frequency equal to twice our signal frequency. This is actually 2 pi 2 ft, right? If we have a low pass filter with a cutoff frequency well below 2f, what happens is that if we pass this signal through this low pass filter, the second term will be filtered out, and we will just have the first term. We call this SILP, which is equal to AM over 2 cosine phi. This is good, but this has two informations in it. It has information about AM, which is our amplitude, plus information about our phase. We want to be able to find these separately. What we do is we go define SQ, which is again the same as before, but instead of just multiplying our signal to a sine, we multiply it to a cosine. Then we can expand this multiplication again using this math. Sine A multiplied by cosine B is equal to half of sine A plus B plus sine A minus B. Then if we use this, we end up with this equation. The first term is, sorry, this is, so this equation becomes 2 pi ft plus 5 plus 2 pi ft. And the other one is subtraction of the two phases. If we simplify this, we end up in the similar scenario. AM sine phi plus sine 4 pi ft plus phi. The second term, again, after if we apply a low pass filter to this signal, the second term will be filtered out, and we will end up with AM over 2 sine phi. We call this SQLP. Now we have two equations and two unknowns, right? We can easily extract the information for AM and phi from these two. How? We just, for taking the amplitude, we took we take the square root of SILP squared plus SQLP squared, which becomes AM over 2, and our phase becomes tangent minus 1 or arctangent of SQLP over SILP, right? Because these two terms will cancel out and will be just sine phi over cosine phi, which is just tangent, right? So now we can have the information of both AM and our phase, right? This this method helps a lot to extract information from very noisy environment when the signal is just not the sine wave, one tone sine wave. It's mixed with noise or other sine waves. But if we just want to find the information of a particular frequency, we can lock our frequency to that frequency and extract the amplitude and phase of it, right? This method is also called creating a locking amplifier. Okay, now let's see if we apply this same technique to a signal that is having three different sine tones, F1, F2, F3, right? I just want to show the beauty of this method, right? Let's say we want to see the information of the second frequency, but this is buried with other tones in this signal, and it's not very easy to do that, right? But let's say we multiply a sine 2 pi f2 to this to our signal. So we end up with three terms. First, I just categorize them based on the amplitude. AM1 will see cosine 2 pi f1 minus f2 minus with phi 1 minus cosine 2 pi f1 plus f2 plus phi 1. The second term, which is for AM2, now sees cosine phi 2 minus cosine 4 pi f2 t plus phi 2. This is very similar to our previous equations when we only had one sine wave, right? Um, the third term is for AM3, cosine 2 pi f3 minus f2 t plus phi 3 minus cosine 2 pi f3 plus f2 plus phi 3. What happens here is that assume if f1, f2, f3 are far enough apart from each other, f1 minus f2 will not be zero, right? Or F3 minus F2 will not be 0. So these tones will not be time constant over time. Also, these terms, F1 plus F2 or F3 plus F2, they also will not be constant over time, right? So when we apply a low pass filter to these, what happens is that we end up with the previous scenario that only this constant term, cosine phi 2, will remain, right? And the rest will be uh, same as before, right? We can apply the cosine wave as well to end up with AM2 sine phi 2 and do the same thing. After the low passing, everything will be the same as only having one tone, right? So this is the beauty of this method because as long as our frequencies are not very close to each other, we can use this method to extract our F2 information um, from the noise or other terms without any issue, right? This is also this, as I mentioned, this method is sometimes called locking up. Now we want to see how we can implement this using our ADALM-PLUTO. Assume that this is the block diagram of AD90-361 IC inside the ADALM-PLUTO. And we can see we have the building blocks here to make our locking amplifier. How? Uh, we have the input at our receiver. We can mux, and then we have a very low noise amplifier here. And after that, we have these mixers, which from another point of view can be seen as just multipliers, right? These are just multipliers creating our SI or SQ, just multiplying our input to a sine of 2 pi ft or cosine of 2 pi ft. Why I'm saying sine or cosine? Because ADALM-PLUTO, as you can see here, we talked about it in our last video, in our previous videos too, generates the quadrature signals for us, I and Q, with these phase splitter from the oscillator. It creates the sine wave and also another cosine wave here, which is 90-degree different from our sine wave. And then it multiplies R and Q, I and Q to our received signal. You see, it's just creating SI and SQ for us, right? We just need to apply a low pass filter after it, right? How we can do this after reading the ADC information uh, after the multiplier and then apply a low pass filter and then extract the DC value which was a SILP and SQLP and use those to extract AM amplitude of the signal and phi, right? And one interesting thing is that these in Pluto are designed to operate in high frequencies up to 6 gigahertz, meaning that our lock-in amplifier can operate to up to very high frequencies, right? Now now that we learned how to create this second approach, how to implement it, and we saw that theoretically how we can use ADALM-PLUTO to make it, in the next video we are going to see in Python how we can, by some coding, we can configure our ADALM-PLUTO to do this for us, and then we look at very cool examples. One example that I want to show in the next video is by just connecting an antenna to the receiver of the ADALM-PLUTO and sweeping this LO frequency. What happens is that when I'm sweeping this LO frequency, at each given frequency, it extracts the amplitude and phase information of that signal in our receiver, right? It extracts it among all other tones or noises from the received signal. And we can use this to see what's going on in the open air around our environment, what signals and at what frequencies are in the environment around us. We see that we can see the wireless Wi-Fi signal, we can see Bluetooth signal at 2.4. We can see LTE signals, which are for cellular communications and etc. Stay tuned for the next video and thank you for watching up to this point. Bye.